If you've ever found yourself staring at a logic puzzle, just grinding through every single possibility and thinking, there has to be a better way, well, you are in exactly the right place. Today, we're going to dive into the smart, the elegant, and frankly, the much, much faster ways to find the truth. So let's just jump right in with a challenge. Take a look at this beast of an expression. Is this thing always true, always false? Or does it depend? Now, I'm willing to bet your first instinct is to reach for one very specific, very common tool to figure this out. And that tool is probably this guy right here, the good old truth table. You map out every single combination of true and false for P and Q, and you just painstakingly calculate each little piece column by column until you finally get your answer. And yeah, as you can see, the final column is all false. So it works, but wow, look at all that work. Yeah, let's just call this what it is, the brute force method. The source material we're looking at today doesn't pull any punches either. It calls this way of doing things boring, time-consuming, and just plain inefficient. And there's a really, really good reason for that. This right here is the fatal flaw of truth tables. The number of rows you need just grows exponentially. So with two variables, P and Q, okay, you need 4 rows. Manageable. But add a third variable, R, and suddenly you need 8 rows. A fourth, and you're at 16. And get this, for just 10 variables, you would need a truth table with over 1,000 rows. It gets completely out of hand incredibly fast. But thankfully, there is a much more elegant, much more efficient approach. So let's talk about a smarter shortcut called the by-case method. The difference between these two ways of thinking is just night and day. Brute force checks everything. It's like trying every single key on a giant keychain. The by-case method, on the other hand, is analytical. It's like actually looking at the lock to figure out what kind of key you need, which, as you can imagine, narrows down your options immediately. And this is the core insight, the beautiful aha moment behind it. Any single variable, let's just call it P, can only ever be one of two things, true or false. That's it. There's no third option. So if we can just test our expression for those two master scenarios, one where P is true and one where P is false, and if we get the same result in both, then we've actually covered every single possibility without building that giant, messy table. And it really just breaks down into 4 simple steps. First, pick a variable. Any variable will do. Then you test the whole expression, assuming that variable is true. After that, you test it again, but this time assuming that same variable is false. And if you get the same answer both times, boom, you're done. All right, let's go back to our original puzzle and actually solve it this way. So, case 1. Let's assume P is true. Now, look at the second half of our expression, not P and Q. Well, if P is true, then not P has to be false. And a really important rule in logic is that anything connected by an and to a false statement is automatically instantly false. So that whole second part just collapses to false. And since our two halves are joined by an and, the entire expression becomes false. Easy enough. Okay, now for case 2. Let's assume P is false. The first part, P if and only if Q, simplifies to not Q, because for them to be equivalent, Q has to be false too. The second part, not P and Q, well, not P is true now, so that just becomes Q. So our whole expression boils down to not Q and Q. And something can't be both itself and not itself at the same time, right? So that is always false. And there you have it. It's false in both cases, which means the expression is always false. So much faster. But what if we could solve it even faster? What if we didn't have to test any cases at all? For that, we need to open up what I like to call the logician's toolkit and learn how to manipulate these expressions directly using a few really powerful logical laws. And the key here is to stop thinking of these as abstract, boring rules you have to memorize from a textbook. Think of them as tools, like a wrench or a screwdriver. Each one has a very specific job that helps you take a complicated expression, take it apart, and simplify it down into something you can actually understand. Okay, first tool in our kit, the distributive law. And this one should feel pretty familiar if you remember any of your old algebra classes. Just like you can distribute multiplication over addition, in logic you can distribute an and over an or over an and. It is fantastic for breaking up things that are stuck inside parentheses. Next up, and this is one of my absolute favorites, DeMorgan's law. I like to call it the flipper tool. It lets you take that negation, that little not symbol, and push it inside a set of parentheses. But here's the trick. When you do, you have to flip the operator inside. An and becomes an or becomes an and. It's an incredible way to rearrange an expression. And finally, we have the absorption law. This is your ultimate cleanup tool. It basically says that if you ever see a pattern like P or P and Q, the whole entire thing just simplifies down to P. It's like the P just absorbs that more complex term right into it. It's an amazing trick for making your expressions shorter in Flash. Okay, so we've got our tools. Now let's put them into work. We're going to use what's called the simplification method to take a brand new expression and just transform it step by step until we get to its simplest form. Let's walk through this one together. We start with not P and P or Q implies Q. Okay, first things first, let's use our distributive law on that first part. That gives us not P and P or not P and Q. Now, think about that first bit. A statement can't be true and false at the same time, right? So not P and P is always false. We can just get rid of it. That leaves us with not P and Q implies Q. Next, we got to deal with that implies arrow. Here's a handy conversion. A implies B is the exact same thing as saying not A or B. So let's rewrite our expression as not P and Q or Q. Now we can use our awesome flipper tool, DeMorgan's law, on that part in the parentheses. We push the not inside, which flips the and to an or and flips the variables. This gives us P or not Q or Q. And now we can just regroup this to be P or not Q or Q. And since something is always either true or not true, not Q or Q is always true. And anything connected by or to a true statement is, you guessed it, always true. So that whole complicated monster of a statement simplifies beautifully all the way down to just true. Now, I know this can feel a little abstract, but these tools are so incredibly important for one huge reason. They give us a way to bring mathematical precision to the messy, sloppy, and often ambiguous world of everyday language. Take a sentence like this, for example. It seems pretty straightforward, right? But what does it actually mean, logically? Is it a promise? Is it a condition? A restriction? The specific words that we use matter a lot. The real puzzle here is, how do we translate this from English into the precise language of P's and Q's? It turns out certain words and phrases in English have very specific logical meanings, and knowing them is really the key to clarity. Here are two of the most common ones you'll run into. The phrase P when Q actually translates logically to if Q, then P. The condition, Q, comes first. But if you see the phrase P only if Q, that flips it. That means if P, then Q. That only if introduces the necessary consequence. So let's apply our rule. A fail grade cannot be given. We'll call that not P. When a student scores over 50%, we'll call that Q. This is a classic P when Q structure, which means it translates to if Q, then not P. If a student scores over 50%, then a fail grade cannot be given. See? We just took an ambiguous English sentence and turned it into a rock-solid, precise, logical statement. And that kind of leaves us with one last big thought. We've seen how easy it is to think we understand a sentence, but how digging into the formal logic can reveal a much more precise, sometimes different, meaning underneath it all. It really makes you wonder, doesn't it? What other common instructions or promises or arguments are we all getting just slightly wrong every single day, just because we haven't looked at them like a logician?